connecting. Okay, so I'm assuming we're in the cloud now. All right. Okay, hopefully that'll work. Thank you for that reminder.
Yep.
All right, so okay, so now the point of this page is this result that we had for the compact trig was pretty much ginned up from conclusions from the previous page, but not directly from, let's say, one step from here. However, you can make a case that you can see in one step how the two are evidently connected. I mean, that's just basically, you know, the cosine of the sum of two angles kind of argument, right? A plus B, right? And so I believe I have that trig identity correct. My memory's not perfect, but I think it's correct. Hopefully when I wrote it down. And so if we see that in the terms which did have a pi, we can think of the general form of any one of those terms as the cosine of something plus pi, right? So whether it's 3t or 7t, it was something plus pi. So for all of those, if you use the cosine of the sum of two angles kind of trig rule here, we can see, since we know that the sine of pi is what? What's the sine of pi? Anybody out there? Should be what?
0.
0, right? So of these two terms, we could say almost immediately, the first one, the second one of those two is going to not be there. Which one is it, first or second?
Second.
Second, right. So we're only going to have the first one. So we have the cosine of A and the cosine of B. But what's the cosine of pi? If you think about it.
-1.
Minus -1, right. So if we use that fact, we see that this result, you can argue going this way might be easier. From this result, you go directly back to the original basic. Just to point out that, well, there's maybe more than one way to skin a cat, so to speak. And I would argue that, you know, you don't have to go, if you can see that, it's in the one you start with is simple enough to do it. Converting to the compact, this would be a perfectly reasonable scheme to use. I mean, certainly in simple cases, it would have, this kind of line of reasoning could be applied legitimately. All right. Some features in the book are really, to my liking, like the way he integrates some of the historical footnotes in there. So I'm recommending that you read this section. I found it very interesting. It has to do with the so-called Rosetta Stone, and our hero here of the chapter, Fourier, evidently played a role in the deciphering of hieroglyphics. Another hero of yours from physics, I would guess, who did the two-slit interference was involved, Thomas Young. I think he's the same Young who did it. And then there's this other guy. You see, I can't get the blow up feature here. I guess I have to have it on Zoom to do that, or have it on slideshow to do that. Let's see. If I have this on slideshow, maybe I can do it from the beginning.
I think at the bottom right of your screen there was a slider you could use to zoom in.
Okay, let's see if we can get that page again. Okay, let's try that again. So all new to me. At the bottom, right? That one right there.
When you were in the other view.
Oh, I could have done it there too, you're saying?
Yeah, I believe so.
Okay. All right. Well, so there you see. I'm pretty sure Tom, I know there's two Youngs out there, but I still think he's the one that did the two-slit interference, if I remember correctly. And this other guy, I think I dropped an L in his name, but it's kind of interesting. From my understanding, there's this great video you can get from the UT Tyler Public Library once they come out of quarantine, so to speak. There's this great video they have there, if you ever get a chance to see it, on the deciphering of the hieroglyphics. It was quite interesting. But what I understand is that both Fourier and Young got involved in sort of cracking the ice on this thing, but really didn't follow through on it because there are other interests in physics and optics, et cetera, and math. But this other guy, Champollion, pretty much just given a lot of credit because he really pretty much fleshed it out fairly completely, the deciphering of that Rosetta Stone. So it's very interesting. Anyway, I guess we go on. And I do recommend it. It's good. It's good reading. All right. Let's go to this one. All right. So we just are that. Whoops. 1, 2. Okay. So from that example, I think it was 6-4 for the repeating pulse. We had this basic trig result, and if you and here's a representation of it right here. And then this is the pulse part right here. Then if you just say what's the DC, which is the first term, that's the 1/2 that runs across it. Then it turns out that if you would, let's say, just limit yourself to the first 2 terms, then it turns out you would get a shape like this. Then if you go to the third harmonic, which would include the third one here, that would be n equal to 3. Then you would have the DC plus 2 terms. It'll look like that. And you get to the 5th, I guess one's for the 5th. Then that would be n equal to 5 for the 5th. Then it starts to take more on the shape of the actual waveform that you're representing. You keep going up, obviously. And it gets better and better as you include more harmonics, more accurate in terms of representation. Although there's this interesting phenomena called Gibbs phenomena, you'll have to read about it. It seems like no matter how hard you try, you tend to get this little bump that never seems to go away. Although it's probably not mentioned in the book, there's an interesting optical artifact for a single slit diffraction that looks almost like the same kind of problem. But anyway, the idea is, if you may catch this here, your next and last MATLAB has now been placed on canvas for you to take a look at and get going. And I believe that'll be due in approximately 2 weeks, a little more than 2 weeks. All right. So, and what will you be doing? Well, you'd basically be recreating the elements of this figure. Okay. So you'll see. So you can actually see where this comes from. All right. Any questions? Okay. Then we go to the next page. All right. Okay, so here's some, I thought, relevant comments to make because we have these 3 types of Fourier series. And it's kind of worthwhile to back up and look at the relationships between them. And you could see that in the basic trig, at a certain identifiable harmonic associated with n times omega naught, you have the terms with a and the bn. If you graduate to the compact, you've got the cn, which looks like that term. If you graduate to the complex exponential, you got those 2 terms, all of which are tied to the specific harmonic n omega naught. And I don't know, I think it's worth mentioning, maybe it's obvious to most of you already, but it's worth mentioning, these have a certain relationship. What are they? Anybody have any wild guesses how these are related? They are all. I'll accept a good guess here. Anybody?
Identity?
What? I didn't
Identity?
hear you. I'm sorry, I still didn't hear you. Can you say it louder?
An identity?
I think what you're saying, they're all equal. If that's what you're saying, you're right.
Yes.
Yeah, they are all equal. And the way to view that is, in some sense, goes back to the ideas of these functions. Different harmonics are independent of each other. So you can't construct a sinusoid at the third harmonic from a sinusoid at the second harmonic. And so the only way those series could all be the same series, the same function x of t, must mean that in fact, what you're looking at are 3 rows of terms, which each row is equal to the other row. Okay, so it might be worth keeping that in mind. And to follow up on that, we would have to argue, since we can look at the first 2 rows and see that the first 2 rows are strictly what? I'm thinking of a word, real, imaginary, or what? They're
Real.
both real. They're both 2 are absolutely real. Therefore, the bottom row has to be real. Now, the only way that can happen, this might be a good time to do a little zooming if I can figure that out. Let's try that here. The only way, you notice that there's the plus there, right? Argument on the exponent, and there's the minus. So the exponentials are clearly complex conjugates of each other. So the only way that the overall expression here, with the 2 terms, the complete set of 2 terms here. The only way that could be true is, in fact, the DNs go along with that story, forcing these terms completely to be complex conjugates of each other. You know, the old argument Z plus Z star is strictly real. So we would argue that the DN and the D minus N, okay, associated with the positive N and negative N, they have a direct relationship that's forced on them by virtue of the fact that some of these 2 terms have to be real. Okay, and the only way that could be true is, in fact, that the DNs themselves are complex conjugates of each other. So the D of a minus N is the complex conjugate of DN. Any questions? Let's see if I can, I don't know if I can do this, but I don't think. Oh, yeah, I can. Okay, hey, that's good. Okay, so now what are the implications? Well, we know that whenever you have 2 complex numbers and they are related this way, that one is the complex conjugate of the other, we know their magnitudes are equal. And we know that they differ, and we know their phases are not the same, but they differ by there should be an equal sign in there. It got left out. See, this is where I wish I had a document camera. I could squeeze that in. Let's see, what can I do with my, I've got a pen here. Let me see. Where's that pen at? Is that a pen there? I think it's a pen. Okay, sorry, I almost wiped out the complex conjugate. Anyway, there should be an equal sign in there. So now what are this is kind of sort of general, let me get rid of that. Okay. So from that, we can conclude that the magnitudes of these 2 coefficients have to be the same because of this basic background that you all know from complex arithmetic. And therefore, if they're the same, we would say that the magnitude of the D to the minus N is the magnitude of Dn complex conjugate, okay, which we could just say, well, we know that that's equal to the magnitude of Dn. Which, in brief, because of that would say, well, as far as the symmetry of this goes, the magnitude operation is an even function because you change n with a minus n, you get the magnitude back. Remember, if you change, like for even function, you would say, well, if you change x with a minus x, you get the same function. Here we're changing n with a minus n, and we get the same function. Therefore, we'd say that dn has the absolute value of dn, or magnitude to be precise. The magnitude of dn is in fact an even function with respect to n. I can't get it to go up or down anymore, so I'm gonna see if I can't get out of this. Get out of this. Escape. How do I get out of this? This page. What does it seem that I see? Okay. Okay, I'm going to hit that and see what happens. Okay, maybe that took care of it. Nope, did not do it. Oh, here we go. Okay, we'll do that. Seems to work. Okay, so now as far as the angle go, it's probably no surprise. You can see that if you replace the n with a minus n here, you're gonna end up with inclusion. Okay, since this follows the same rule as up here. The inclusion that there's a minus sign put in for the complex conjugate one, as it relates to the original one, and therefore it has odd dependence. So it's basically on n. So we see even and odd come up here. Dog here. All right. Okay. So now if we represent the dn complex coefficients in polar form, we can use, obviously it has magnitude and phase. And where we're gonna go with this is we're gonna plug that in to our general representation for the complex exponential as we see it here. Okay, so and specifically we're gonna break out the harmonic two terms that are the same n omega naught. So basically I'm thinking, okay, I'm only looking at two of the terms in this infinite sum. And in doing that, you have to plug in for the dn's, okay, for the two cases. So you would say, okay, there's when the n is negative, okay, then we have that term that's from that sum, and when the n is positive, we have this term which is from that sum. But they're both tied to the same harmonic, n omega naught. So that's why they're included. So what we'll do is we'll formally plug in what we've got here, and we could argue, and we've already established that the magnitude of since the magnitude is an even function, whether I write dn or d minus n subscript doesn't matter. I mean, technically I could have put a minus sign here, but I think clearly I'm using the even property already here. And then there's e to the minus j theta n, since the we already established that since it's complex conjugate, when it's plugged in, I have to use the, I can then replace the j with a minus j, and then we see the minus j pop in there. And then the rest of it is just like you see it in the original part right here. And there's your second term. This one's, of course, the pretty much just by substitution, dn, right? From here. So just to recap, in the first term, we had to use the properties from up here of the magnitude of dn being an even function and the phase being an odd function. Here we just plugged it right in. It was good to go. Then we can factor out the dn from both terms and divide by 2. You can see where this is going. We want to head towards one of our famous sine functions. And I guess specifically, it looks like it's going to head in towards the cosine function, right? Because you got the right arguments in place, one with a minus j and one with a plus j. So that becomes the cosine function. Notice the 2 is absorbed in that process, and still have the 2 in front here, so that had to remain. And this is at a point where we come back to the idea we had earlier, is that, well, these harmonics are in a sense independent of each other, so each of the rows above have to be the same. Whoa, that's not what I wanted to do. Let's see if we can get back to that. So as we can see, we're saying this row has to be the same as that row. Therefore, we got done manipulating this row into a form that we liked, and we're going to compare it with this one up one row above. The dogs are driving me nuts. Okay. All right. Any questions so far? So this is the kind of the punchline on the story. That equal sign doesn't belong there. Where that was, I don't know why it's dragging along. Anyway, the punchline of the story, these are equal. And the only way they could be equal, since the cosine part's the same, would be the coefficients in front have to be the same. So Cn has to be equal to then 2dn. And and we can say, well, you might say we're happy if you just told you to believe it, but we can go back and look at our table, and that should be in agreement with our table. Somewhere in that table, we got to see, oh, there it is right there. There it is right there. And we already talked about C0 is equal to D0, so I'm not worried about that. Okay, let's go ahead. Okay, so we got this example from the book regarding computation of the dn coefficients. Let me get rid of this. Where's that eraser when you need it? Let's see. That worked. Okay. Okay, so here is the problem is the so-called, often called the comb function, by virtue of the fact that, of course, reminiscent of a comb. And it's defined in a way, it's basically a repeating, some people call it impulse function or delta function. Okay, so you notice the subscript here identifies the period. And technically speaking, if you wanted a, let's blow that up a little bit. It's not showing. There it is. All right, so yeah, if the T naught is the period for this function. And what we want to do is find a way to represent the x of t as a Fourier series, exponential Fourier series specifically, and come up with a d sub n. All right. Now we can pull up our recipe for the computing the exponential Fourier coefficients, one we came up with earlier. It's also on the table, I believe. And we see that we can elect to take whatever window of time as long as it's a time span t naught. So what is typically done here is to imagine a window of time that essentially, draw a little sketch on the tape. Essentially just oops, that's not what I want. Okay, like that. So that's actually, so a window of time that includes from minus t naught over 2 to t naught over 2. So if we assume that is our preferred window of time for the calculation, then we can see that within this window, the function is 0 everywhere except at 0. Hopefully you recognize that. And in fact, it simplifies considerably because there's only one of them at 0. One delta function at 0. Dirac delta function. Okay, so all we need to do is complete this calculation. But we know we know how to evaluate integral functions involving delta functions. That's where we had spent some time in chapter 2. And I would say you can see what do you do here? Where do you need to evaluate this function, the exponential at, for what value of t? Anybody out there? What value of t?
T
Which
naught?
is t equal to, not t naught. Think where is the singularity for the delta function? T equal to
Oh, 0?
0. Right, 0. So to think of t equals 0, you're going to evaluate that at t equals 0. Then what does the exponential become?
1.
1. Right. So all you're doing is using that so-called sifting concept that went back to the original introduction of the integration with delta functions. And so you just evaluate the function where the singularity is, and that becomes the value of the ultimately of the integral itself. So you basically replace that whole integral with simply 1. So the coefficients become 1 over t naught. And so as simple or as complicated it is, once we have that, and that's true, and notice there is no n dependence in this one. That's what makes it really simple, is it doesn't depend on n, although there's another example later in the text that does depend on n, but this one does not. And so the n is the index, but it's the coefficients are exactly the same, real, positive, 1 over t naught for every n. And so it can just come out front. All right. Okay, let's see. How are we doing here? No, we're okay. Okay, let's go down the page here. Doesn't want to go down. Let's see. Why not? Let me see if I can move it down. Nope, can't move it. I got it. Let's get out of this. No, maybe I can. Ah, yeah. Okay. Okay, so we can construct, let's say, the compact trig series for this. Now, I would argue that, at some point we're just going to become more comfortable relying on the table for guidance. And so let's see if we can find these rules. So the C naught is, we know C naught is D naught is equal to A0 because that's always the constant of the series. So that's going to be true. So it's going to be 1 over T naught. That one you don't need the table for. We just established this one from the previous page. Therefore, to get the Cn, all we need to do is take 2 times the magnitude of dn, but since the dn up here at the top is strictly positive real number, we can just say, well, that's equal to 1 over t naught times 2 for n greater than 1. So we've got our Cn, we got our d naught. Now we can check here. It's like I said, at some point we want to look at rely on the table. It says we did our analysis, we would find that the an is directly predictable from the dn. And we can, let's go take a look at the table and see where that came from. That table is intended to be sort of a composite of all the important formulas for which we need to relate these. There it is. Okay, so let's go here. So you can see that, let me see. Right. Here it is down here. I mean, I guess I've added a few of my favorites because I felt like they could be, come in a pinch, they could be helpful, like right now. So the AN is 2 times the real part of DN. It turns out that I think that's pretty useful. And we got the one for the BN here too. So keep this one in mind. We can see that DNs were real, so don't be surprised when the DN was strictly real. So don't be surprised the BNs will be 0. But the ANs won't be 0. We'll see. Okay, so that takes care of that. Let's get out of this, see if we can. All right, let's go forward back here. I think I went too far. All right. Okay. Not sure where I remember where those came from. So I can erase that here. Okay, so we can see that we've already talked about the C0 that we need. Okay, the Cn is 2 times the magnitude of Dn, but Dn is real and positive, so I would argue it's just equal to the 2 times the Dn, which we found here at the top is, where do you find it? There it is right there. Dn is 1 over T naught. The AN is 2 times the real part of DN, but DN is strictly real and positive. So again, it's AN is equal to 2 times 2 over T naught. And the BN, as we talked about, would be 0. So so we can then get we can get the theta n, the angles that we need up here by noticing all the AN will be what sign? Anybody follow me along? All the AN would be positive, and then all the BN would be 0. So we'd say that using the same logic we had before, the first term will all be BN over AN is 0. So the inverse tangent is 0, 0. And because you only get the pi when the AN is negative, but all the AN are positive, so the conclusion is all the theta n would be equal to 0. And therefore, the complex exponential Fourier series would reduce to this form right here. Any question about that? All right, let's see what I got on the next page. Whoops, how can we go to the next page? I don't know. Should go to the next page. Let's try again. Page down. I'll get to the next page. Oh, here we are. Okay. So if we had looked at the spectrum for these two in terms of Fourier series representations, graphically, we would see, of course, a discrete spectrum because there's really only signal at the harmonics, regardless of whether it's the exponential or the compact. And we see, in fact, in the case of the exponential, that's where we use, this is kind of like why the complex exponential is the bootstrap to the Fourier transform, is because we have both the positive frequencies and the negative frequencies. Not that they exist in the laboratory, but from a mathematical viewpoint, they're useful. And we see the compact Fourier series here only shows the lines on the positive side, not to confuse you, but we never, for the compact Fourier, the n values are strictly greater than or equal to 0, so we don't even bring up the issue of negative frequencies. Both of them have the same D0 and C0 are the same. Other than that, we see that the compact coefficients are twice as high. You could argue without proving it, you could argue, well, that kind of makes sense because you're saying all that I mean, technically power that's in that Fourier series up above has to be accounted for below. So it does make sense that you have the stronger coefficients because you're representing everything going on the positive frequency side with a compact. With a complex exponential, you're using both sides. Did I confuse you on that? Any questions? Are there any questions? All right, let's see. Where are we on time? 5 minutes or 2 minutes? How much time we got left?
2
minutes.
How much? I tell you what, only 2 minutes won't get me very far on this page. I'll tell you what, I'll pick this up on Wednesday. Now remember, I think our plan was I'll keep this line open for 15 minutes today. If you got some follow-up questions, and you can start right now if you want. If you have a question, but as far as the rest of the class goes, if you don't have any questions and you got other things you got to do during the day, I'm gonna pick up Wednesday's discussion on this page. Parsable term. All right, so I'm not going to end the meeting. I'm going to try to leave this open for 15 minutes. So if you have some questions, this is a fair time to do it.
Yeah, paper.
Yeah. I can't hear your question though. I hear the dog.
What was the was there a value for T
For
naught?
some reason, I'm not hearing your question. You can hear me. Yeah.
Was there a value for T naught on the physics example that you went over?
I don't believe there was. As I remember correctly, in this example, there was no numerical value given, although it could have been. It didn't have. I think it was left sort of like, well, okay, well, the what might be considered the tough part of the problem was done. As I remember in this example, there's no there. See, let's take a look. Here's the details up here again that goes with the example, and I don't remember a specific T naught being specified.
Okay. And why was on the second line? Why was it changing to an exponent?
On the second line, I use my pointer here, and you tell me if I'm on the right line. Will you say second line here or down here?
On number 2.
Number 2, okay. And so, what's your question?
Why was it? Why was it changing to an exponent again?
Exponent. Oh, you mean this representation, or?
Yes. Yes.
Oh, okay. Well, this goes back to the idea that we're wrestling with, and I don't like things simultaneously, but we're wrestling with 3 different forms of Fourier series. And this is the form for what's called the complex exponential one. And I'm not, it may be completely misunderstanding your question, but you need to clarify if I am.
Okay, no, yeah.
I mean, so in some sense, it's not like it's derived or anything. It's sort of like, okay, well, this is the given form that we're going to take for the complex exponential Fourier series. And that's how it's defined in a way.
Okay.
Other questions? Yeah.
You said the x of t, the original one, the one from the graph.
The one from the graph. What do you mean, up here at the top, or?
Yes, on top, yes.
Okay.
You said the singularity function was 0?
Yeah, I referred to any, the places where that you've got the delta functions. Okay, it's basically a repeating periodic delta function, is what it is. And where you've got them, I would refer to those as singularities, because the arrow is supposed to remind us it blows up there. In other words, it's not. You can say it's not defined, but you can say, well, we can think of it going to infinity. So it's kind of like in the vernacular, sometimes used, it might be called a singularity.
Oh, okay.
Other questions? Just to remind you, you do know that the window for the, I think it's quiz 4 for this class is in fact open all day tomorrow. Or is it all day or till? No, maybe not all day. Maybe it's still, I'm thinking it's still I'm thinking still noon or something. Anyway, you may want to check when that, I think I wanted to close it halfway through the day tomorrow. So you may want to get it knocked out today if you have a chance.
Oh, okay.
That I believe that will be quiz 4 posted on Canvas. And that's associated homework 4. And I brought my quiz blank with me in case you had a question about it, but I can't tell you how to do any of them anymore, but I can, if it's a matter of interpretation, I can try to help on that. You say, well, I don't know what the question is asking for. In that regard, I can possibly help.
Real quick, sir, sorry to bother you, but quiz for the deadline shows up as March 31st, which is tomorrow at 11:59 p.m., not a.m.
11:59 should be, I think I meant 11:59 a.m. But you're saying it shows up as 11:59 p.m.?
Yes, so 1 minute before
Before midnight.
Yeah.
Okay, let's leave it that way. I'm not going to mess with it. Thank you for that correction.
No
that
worries.
means you got all day tomorrow, right?
Yes.
Yeah, technically somebody has all day tomorrow to work.
That's
on it.
right. That's fine. Thank you for that. I thought I wasn't sure when I answered the question, but I appreciate that, and I'm not going to change it. And I'm so because it's fine with me. It'll work.
Also, for the other classes too, that is auto controls. I know we're not in that class right now, but those times are also 11:59 p.m. for the quizzes and the quiz 5 and the MATLAB.
Yeah.
Okay.
I think that one is for today, right?
Yes, sir.
Yeah, that's fine. That's how I intended that one to be.
Okay.
Guaranteed. That's how I intended it to be.
All right. Sounds good.
Okay. Other questions? Not from my dog. Thank you. All right. Any other questions?
Right now, I don't think so.
I didn't hear that. What was there?
Right now, I don't think so. Did you hear that?
No, I did not hear.
No, I don't have any questions.
Okay. Okay. All right. Well, if I don't hear any more questions, then I may. Okay. Well, if it's okay with everyone, I'm going to close the meeting. I'm not sure if there's no more questions.
All right, Professor. Thank you.
Okay.
Okay. All right. Great. I'll talk to you later.